Right, madam. We'll start, madam.
Okay, sure.
Sir.
Respected today's resource person for our third day first session, Dr. Aruna Malapati garu, who is professor in Department of Computer Science. Respected today's resource person for our third day first session, Dr. Aruna Malapati garu, who is professor, Department of Computer Science and Engineering, Pilani, Hyderabad campus. Director Dr. C. Viswanadha garu, my coordinator Dr. K. Rameshwara garu, and Dean School of Pharmacy and Dean School of Management Science and other HODs of various departments, my dear faculty members, very importantly, the participants of this program. Very good morning to all of you. Warm welcome to this session. It's my really privilege to introduce about today's speaker, Dr. Aruna Malapati, presently working as professor in Department of Computer Science and Engineering, Pilani, Hyderabad campus. In the past, Madam has worked at different capacities as associate professor and even senior lecturer, and in fact, Sir is having very good experience on software platform as senior software developer at ISTE-STTP Limited, London. Madam was also a visiting researcher, Centrum Iskunde and Informatica, CWI, Netherlands, since 8 June to 31st July 2015, which was funded by Pilani and Raju University, Amsterdam. Senior software developer, ISTE-STTP Limited, London, UK, October 2002, December 2001. Madam has published 40 journals in high reputed and impacted journals, both in national and international journals, including conferences. Madam has very good number of awards in her credit. Let me read few of them. Madam has received Professor Indira Parikh 50 Women in Education Leaders citation at 6th World Education Congress on 23rd November 2017. Madam received Women in Education Award from the Devang Mehta National Education Awards on 15th April 2017. Madam also received the Best Paper Award runner in IK 2013, which is 5th IBM Collaboration Academia Research Exchange for the paper titled Comparative Study on Effectiveness of Standard Bug Prediction Approaches. Madam was the finalist for INAE Young Engineer of the Year 2019. Conclave invitee for Google India Women in Engineering Award in February 2008. Madam also received Best Paper of the Year 2008 in the Computer Science Engineering section at Annual Technical Session by Institution of Engineers, AP State Center. Madam also received Young Engineer of the Year 2007 award from Andhra Pradesh State Government and the Institution of Engineers, AP State Center. Madam also received Best Paper of the Session Award for presenting a paper on data mining approaches for in silico drug design in the International Conference on Systemics, Cybernetics, and ICSCI 2005, organized by Pentagram Research Center Private Limited in January 2005. Madam has funding project in her credit, which is worth of 10 lakhs. The product title is Smart Traffic Analytics for Hyderabad City, funded by Pilani. Madam has one more project, which is on credit analytics. Areas of interest are big data, data mining, information retrieval, bioinformatics. With this little introduction, I warm welcome you, madam, for our today's session. Thank you, madam. Thank you very much.
Thank you, sir. Thank you very much for
consent and for sparing your valuable time with us, madam. Thank you.
Thank you, Janardhan, sir, for this nice introduction.
Thank you,
a good morning to all the participants, and I thank the organizers for giving me this opportunity to share my knowledge in this particular area. And amidst this pandemic, you actually have taken such a nice initiative to keep people engaged and have the latest technologies getting exposed to them. So with this, let me start my session. So can you make me the host so that I can?
Yes, madam. You made co-host, madam.
Yeah. So is my screen visible, sir?
Yes,
okay. Yeah. So without any further delay, let us start with this topic, that is supervised learning. So before we get into supervised learning, let me show you what are the topics that I'm going to cover. In the interest of time, if time permits, I will cover all of them, and otherwise, let's see how much we can do. So to start with, first of all, let us try to understand what is the difference between traditional programming and machine learning. Why is this machine learning treated differently as compared to the traditional programming? So what happens is in your traditional programming, you have a problem, and what you are writing is the logic that is written in the form of a program, and you also input the data, right? So you have a program which solves your problem. You give certain input, and then the system outputs what you are expecting, right? But whereas in contrast, when it comes to machine learning, what you have is you are giving it a bunch of examples, right? So basically, so can you make everyone to just join the meeting instead of making me admit them? Is it possible, sir?
Madam, we are taking care of all this.
Okay, fine. We are taking care. Okay. So you can see that in the second part of the figure, what you have is you have the data, which is basically the examples, the training examples that you want it to learn. And you also basically give what is the output you are expecting. And the funny thing is, actually the output of this is a program, or rather most of the time we call this as a function. Okay, so what it basically tries to, you have the input, that is the data, and the output. You're giving both. And what this program is trying to do is basically, it's trying to map these two and basically try to learn a function f of x, which basically maps to y. So if y is your output and x your data, it's trying to learn this function f of x that maps every x to y. And that's what it's trying to learn and output as a function. It's giving you this function. Actually, the funny thing is, you don't have to struggle. Unlike your normal traditional programming, we break our head to write a program and the sequence of steps it takes to solve the problem. But the funny thing here is you give input, you give the data, you give the output what you're expecting, and the system itself figures out what is the program. It figures out rather what is the logic. Okay. Now with this understanding, let us see what are the different types of learning. As the topic is supervised learning, so I started with why learning, how is it different from traditional learning? Now you see that traditionally we put them into two buckets. The first bucket is called as supervised learning, and second bucket is unsupervised learning. Now let me give the difference between these. So what you are given is, as I said, input and output, right? So I will use this notation. So I'll introduce you to this notation. So you have the notation that I'm using is xi comma yi, where I is running from 1 to capital N. Okay, and what is this? Now, as I go along, I will tell you what is this y and what is this x. So for supervised learning problems, okay, you have this sort of a notation where x is given and y is also given. That is, this is data and this is your output, right? So you have your data and the output, and the system is trying to learn this function as I mentioned. But what's the difference between these two? When yi is not given, you're only given xi and asked to figure out how many clusters are there, right? So in such a case, we call it unsupervised learning, which I'm not going to talk about. Let me restrain only to restrict myself to only the supervised learning. Now again, here I am talking about two techniques, that is classification and regression. How these two are different. Now here, when your yi basically is a continuous value. Okay, so when your yi variable is a continuous value, which means, for example, the price of a house, or for example, how much sales you would get, right? So it's a continuous value. Whereas if yi is a discrete variable, okay, if y is a set of discrete variables, for example, you say, okay, whether this guy would take a loan or not, okay. So you have only two values which your y can take. So such kind of variable, we call it as discrete variable. Whereas if you have a continuous variable like temperature, pressure, blood pressure, and things like that, which can height, weight, right? So if these kind of things are there, we generally call it as continuous variable. So when your yi is a continuous variable, we simply call this as a regression problem. And when yi is taking a finite set of values, right? When it's a finite set of values, we call it as a classification problem. Very, very simple. Okay, is that clear? Should I go ahead? Okay. So any queries, you can put it in the chat window. Every 10 minutes, I will just stop and then go there, so that I want the things that I talk to be synced in when I explain. Okay. So this is what I said so let's try to see first the regression kind of a problem. So as I mentioned, you have xi comma yi. So you have n such examples. Okay. You have n such examples. So this is your x and this is your y. So number of training instances are n. That's what I'm trying to say. And so you have some y value. Okay. And what the system has to do is it basically has to map f of x, because this is the input. So it tries to map f of x to y. Okay, where y is a continuous or real value. That's what I mentioned. So you can think it like a floating point in our traditional C programming. If it is a floating point value, then it has to be, I mean, it need not be strictly floating point or an integer, but traditionally we say it's a continuous value. That's how the terminology we use. Here's a very, very simple example to show what is an application of this. So in US, when you apply for higher education, so you can see that what they're trying to do is, given your high school CGPA or percentage, they are trying to see, using this CGPA, right, what might be your university CGPA. That means the input that is given here, X, is basically the high school CGPA, whereas the Y variable that is given is the university CGPA. Is that fine? Another example I can give is, you have, let's say, amount that you are spending on advertising, and towards the Y is the sales. So how much amount you're spending? So if you spend, let's say, 1,000, let's say 1 lakh. Let's put it as 1 lakh. So I'll say 1, 2, 3, 4. Let 1, 2, 3, 4 represent lakhs. Okay. So you have X direction amount that you're spending, and Y direction you have the sales, how much sales you are making. Okay. So let this also be 1,000, 2,000, and so on. Okay. Let that be the scale. So it says that if this is my line, so it says that if I'm spending, let's say 3 lakh rupees, then the amount of sales that you are making is 3,000 units. Okay, that's the notation. So with this understanding, so another example could be where it can be used, could be, let's say you have square feet. Okay, and Y direction is amount. So suppose you are calculating for how much square feet, what is the rental amount. Okay, So if it is 1,000 square feet, 2,000 square feet, 3,000 square feet, and y direction is basically, let's say 20,000, 30,000, 40,000, and so on. So if there is a line, something of this sort, then probably if I have 3,000 square feet building, what is the rent I can expect? So these are some examples of regression. Now let us try to formulate first of all this problem and try to see how it can be solved. So I will be doing a little bit of math here, but stop me if it's getting over your head. So you can see here, I'm showing a line, right? So can somebody tell me what is the equation of a line?
Y is equal to mx plus c, ma'am.
Yes, good. So you have basically, a second. Yeah, so y is equal to mx plus c is the equation of a line, right? So what we do is fine. So let us call this as y dash or y cap equal to mx plus c. So what is this y cap? So here m is basically the slope and c is basically the intercept, right, of this line. So what is the meaning of this slope and intercept? Let me show you. So if you have a line like this, right? So it says that for, so if this is advertising 1 lakh, 2 lakhs. So 1 lakh, 2 lakhs, 3 lakhs, and so on, right? And this is the sales. Let this be sales. And each unit, let it be 1,000, 2,000, 3,000. So here, what I'm saying is for a unit change in X, right? For a unit change in X, how much is Y changing, right? This one. For a 1 unit change in X, how much is Y changing, right? This is basically the slope. And when our X equal to 0, okay, when our X is equal to 0, what is the Y value? Where is this line touching Y, point, right? So this point is basically called as intercept. Now, what is the meaning of this intercept? If you see this example of advertising versus sales, it is saying that even if you don't spend a single penny on your advertising, you will have at least 1,020 or something like that odd sales, unit of sales. That's the main. I hope the things are clear with this. Should I go ahead?
Yes, ma'am.
Okay. So now that you understood what is the meaning of sales and slope and intercept, now let us try to see why did I say Y cap, right? So what we're trying to do is, so given this training examples, so let's say you are given this advertising and sales around 1 lakh training examples. So what we tend to do is, okay, we will split this into 70,000 examples for training and 30,000 examples for testing. This is a traditional thumb rule that we follow, 70 versus 30. So with this 70,000 examples, now what happens is, okay, we try to fit a line. Okay, so what we do is we try to fit a line with this 70,000 training examples. Now, in order to fit a line, so let's basically try to see how to fit this line. So, so in this particular case, another thing that I would like to mention is, okay, let us fit a line, then probably I will talk about this. So this is an example. So 70,000 examples are there, bunch of examples like this. Okay, so if your best fit line is something like this, okay, using the 70,000 examples, I'm fitting this line. Okay, now how this line would help us? Now here, if there is a test example, so these are all 70,000 training examples. Now let me put this as a circle so that we represent the test example. So when there's a test example, okay, now I want to say how much would be the sales if this is the amount that I'm spending, right? If that is your question, then probably you can use this line. So you have already y cap is equal to mx plus c. So you know what is m in this particular case. If this is already fit, what is the slope and what is the intercept? So just replace the x value, whatever is the corresponding x value, you will find out the predicted y cap. So that is why I'm writing this as predicted. Y cap means my predicted value. Okay, but you already know that what is the y for this corresponding test example, right? So we are trying to see how much this predicted value is deviating from this actual value, right? And that is what will drive our entire optimization problem. So our cost function will essentially be 1 over 2n into sigma I is equal to 1 to n y hat minus y whole square. Now, what is the meaning of this? So in this particular case, let me come back to this cost function. If you don't understand, don't worry about this. Okay. So I drew a line in this form. Is this the only line which can fit, or there are multiple lines? Can somebody answer this? Why did I draw a line like this?
There can be multiple
lines, right? So you can have a line like this, you can have a line like this, you can have a line like this, and so on, right? But which line are we going to pick up? Okay.
The line which is in between our the line segment we consider generally between the required points.
Yes. So how do we say that mathematically? So what I'm trying to say is, once these training examples are fit on this particular line, so I have to say whether this is the best line, this is the best line. Let's call this as L1, L2, L3, and L4. So there are 4 lines, and innumerously multiple lines are possible, right? So now what I'm going to do is a simple exercise. So let our M be, let me make C is equal to 0. Now when I make C equal to 0, the meaning is that the line is passing through the origin. Agreed? Because we just now said C is the intercept, which is the point that is when x equal to 0, what is the y value? Okay. So let me make C is equal to 0. When I make C equal to 0, the line actually passes through the origin. So which means my new model y cap will be mx. So now let me take some m value. Let me make it as 0.5. Now, if I ask you what is the cost that this line is giving us, okay, let's try to do this small exercise. So y cap basically would be, so first let's make it as 1 so that we come back to this later. If m is equal to 1, then your x will be 1, right? For 1, 2, 3. So when x is 1, when x equal to 1, 2, 3, if this is your training examples, okay? So x equal to 1 means m is equal to 1. So y cap will also be 1. When x equal to 2, okay, when x equal to 2, right? So our m is also 1. 1 into 2 would be 2. Y hat equal to, when x is equal to 3, 1 into 3, which will be 3, which means the points are this. Exactly. Now let's do a small exercise. Let's make m equal to 0.5 now. When m equal to 0.5, so when x equal to 1, so your y cap would be 0.5 into 1. Okay, you compute that. 0.5 into 2, y cap would be 0.5 into 3, right? So now let us compute what is a cost function for this guy. So the cost function for this particular line L1 with m equal to 0.5 and c equal to 0, the cost function would be 1 by 2 into 3, right? Right? Into 1 minus 1 plus 2 minus 2 plus 3 minus 3. Okay, so the cost function here becomes 0. Whereas in this particular case, what is the cost function? So the cost function would be 1 by 2 into 3, that would be 6, okay, into 0.5, that is your basically the m value, okay. So that would be this value. 0.5, this would be around 1 and this would be around 1.5. This is your predicted value. Predicted minus actual value, isn't it? So this would be 1 minus 2 whole square plus 1.5 minus 3 whole square. Okay. And the cost function would be around 0.58. Okay. So now you can see for different m values, you are getting a different cost function. And hence, what we would like to do here is, so let me draw a new figure that helps you understand how to decide which of these lines is good. So we have basically the m value, m equal to 0.5, let's say 1, 1.5, 2, 2.5. We are selecting multiple m values. And here is the cost function. Let us put this cost function as a function of m. Okay. And so what happens here is when m is 0.5, so our cost function is 0.58, right? Maybe something here. You see a 1, 2, and so on. Okay. And when your m value is 1, the y value is essentially 0, right? So you keep changing multiple m values and you get a corresponding cost function. So generally, when you actually observe, you might have a curve like this, which you must have seen. Okay. As m changes, you would get the cost function, which is a convex function like this. Okay. What is the meaning of this? So this is what is called as gradient descent. Very, very simple idea. I hope you understood the cost function. Actual minus, it's simply nothing but sum of squared errors. Okay. So what you're doing here is that for multiple m values, you are trying to compute what is the cost that line is giving you. And we pick up such a line that gives us this minimal cost function. Okay. And here you can see that my m, the cost function is minimal when some m value, right? So this is basically called as the global minima. This is called as global minima. Okay. Now, you may say, okay, I know how to compute it, but how will the system figure this out? And how do we proceed? So what we traditionally do is, okay, we start with some random m value. Okay, let the random m value be something here. Okay, let it be some minus 0.5, let's say. Let the random value be 0.5. So what we essentially do is, once I know this as the cost function, what I basically have to do is come up with this. Let me show you a theorem. So what this theorem says is, if you start with some m value, okay, so this is my original m with which you have started, and you might have to basically, so you have this cost function, right? So which we called as g of m. Doesn't matter, you can call it as f of m also. So here, what you do is you take the derivative of this cost function g of m with respect to m. Okay. And then you have some parameter which is called as alpha. I'll tell you what is this alpha. Since I do not know. So the idea here is, you're just thinking that, you're going through the hill downwards. But the thing is, you do not know how many steps you need to take in order to go to that bottom of the global minima. So you take you can make one jump from here to here, right? Or you can say, okay, I'll go very slowly. So I'll take 1 step, 2 steps, 3 steps, 4 steps, right? Now this step is basically your alpha. what is the length of your step to reach the steepest bottom is basically your alpha, which is basically called as a learning rate. Okay, which is called as a learning rate. So what happens here is that you may ask me, I can start from here also, right? So it does not matter. So in that particular, even if you start from here, you basically have to, so one thing that you remember is if I'm starting from this side, then I should increase the C value. If I'm starting from this side, I should decrease the C value, the M value, right? Where if I randomly start here, I need to go to this bottom, right? So which means I started with something like 2.2, then I need to go to 2, then I need to go to 1.5, which means I need to decrease if I'm starting from here. So the important thing to remember is this derivative will tell us in which direction I need to go, whether I need to increase or whether I need to decrease. That is what this function is telling. So when you want to basically decrease minus of minus, so you'll have a positive value. So you'll have a positive value so that you come down here. Okay, so it's pretty simple. Is that clear? So for whatever line this cost function is giving minimal, okay, the line that gives us the minimal cost function, we will select that line to fit our training data and we will use that as a model. Our model itself is a line in this particular case. Why? Because once you fit this particular line, so if you have sales, as I mentioned, so you're putting how much of money you're, how much amount you're putting in advertising versus sales. Okay, once you know that my line y is equal to 16, I don't know, x plus 200, let's say. If this is your line, once this is your function, right? I said your system is going to learn this function. Once it learns this function, so let's say you give me, so tomorrow I will come back and tell you, okay, my x value equal to, I don't know, 50,000. I put 50,000 in advertising. Now tell me how much of sales I'm going to get, right? So what you'll do is basically just replace this with 50,000 and then you get what is your y value. Very, very simple. That is how you are going to use this for unknown values, because your training examples might not have all the examples. So what we try to do is we will basically, once this function is being learned, it's very, very simple for us to predict the unknown values. Okay, is the concept clear? Any queries till this point? Yeah. Yes. Yes, Bhavna, you're right. Okay, any queries still here?
No, ma'am, everything is clear.
Okay, fine. Fine. So now let us, so some funny thing happens here. What is that? Let's have a look at it. So what happens is, till now, what we have seen is fine. I was very happy that we were able to get, so this was our training example. Just assume that I have only 2 training examples for some hypothetical case. I fit this line, okay? Now, what happens is when I fit this particular line, so when I fit this particular line, when you have a test data, when I have this particular test data, something funny happens, okay? So, so here, when the test data is actually implemented, you might tend to see that the error on the test data is too high. Okay. One more thing that I would like to, before we get into this, one thing that I forgot to mention was about the learning rate. So how to fix this learning rate? That means whether to take a smaller steps or larger steps. Let me finish that and then go to the next topic about what I would say overfitting or underfitting problem. So if alpha is equal to 0.001, let's say, okay. Now what happens is you're taking smaller steps to reach the global minima. But let's say if my alpha equal to 1, so what will happen is if you are fitting higher, taking higher alpha values, you actually take a jump like this. Okay, and you'll never be able to reach the minima. And that is why it is said that to have lower alpha values is always preferable. So, but you reach the minima. Otherwise, what happens is greater alpha values may basically take you towards this side. And when you take a derivative from here, you come to this side and you toggle between these two and never be able to reach the global minima. So this alpha is one of the hyperparameter that you need to keep changing and see what works better for the given data set. Okay, that is one thing I forgot to mention. Now, I was speaking about once the training data is being fit, whether we would prefer, the errors that should be, there are two things that we should remember. Number one, what are the number of errors that we make on the training data and what errors we make on the test data, fine? So ideally, a very, very good model basically should have low training error as well as low test error. Okay, this is basically whenever you say my model is optimal, okay, a model will be called optimal when you have less training error and less test error, both. So this is also called as low bias and low variance. Okay. We always prefer to have such a good model. Fine. But the problem here is when your model tries to learn each and every example of the training data. So when such a situation occurs, you will notice that the training error is almost zero. Okay. The train error is zero, which means you have fit all the points. And because of which, the minute you apply it on a test example, it will not be able to classify because this is called as overfitting, which means it is learning each and every example in the training data. And because of overfitting, when you have a test data set, it might not perform better. Or in the other, vice versa, you might also have underfitting. Okay, the meaning of underfitting is that it is there is basically a high training error. Okay, so what happens because of underfitting is that your model is not even generalizing the test examples, training examples. Okay, now with this understanding, how do we solve this particular regression problem? What I showed you earlier was a simple linear regression problem, but in order to come up with or in order to overcome this overfitting problem, we would talk about something called as ridge regression. Okay, so what is this ridge regression? So what you penalized earlier is our model or the cost function simply had 1 over 2n, where n is the training examples, number of training examples, y hat minus y whole square. That is predicted minus actual whole square, right? This is your cost function. So what we are going to now do is, now why this happens, why this overfitting happens. Now you see that there's a line which is like this, another line is something like this, let's say. Okay. Now tell me which of these lines would have the slope which is very less. If this is L1 and this is L2, obviously L2 would have a lower slope. What do you mean by slope? For a unit change in X, how much is Y changing? So if the slope is too high, which means that for a unit change in X, the Y value is too high. So you can see this much is the change. Whereas if you see here, only this much will be the change. This will be the change in Y, which is very small, right? So the cost function till now hasn't penalized on the line. What it penalized is only if it is if it is not fitting the training example. Now, what we would like to do is we are now going to add something to this, which is called as a factor alpha or lambda rather into slope the part 2. Now, what is this? So this is your linear regression. Okay, and this part, when you add, this is called regularization. Okay, L1 regularization and L2 regularization. So when it's L1 regularization, it's called as ridge regression. When you apply L2 regularization, it's called as lasso regression. So what is this doing? Okay, now let's consider if you do not want this part, you can make alpha 0, right? When alpha becomes 0, this part is completely 0, it becomes a normal linear regression. Now, if alpha equal to 1, let's say, sorry, lambda equal to 1, let's say. Okay, let lambda be 1, and if the slope is, let's say, 1.3. Okay, just for simplicity, I'm taking some values so that you understand why this helps in controlling that overfitting problem. So obviously there is some value from the linear regression, and what you will be adding is 1 into 1.3 to the part 2, right? So which means just assume that in the first example where we took C is equal to 0 in the previous slide. So here you can see in this example, you could see that the cost was completely 0. Let us consider this example and the cost is 0. Okay. Sorry. Yeah. Let us consider the same example and the cost is completely 0. So when the cost is 0, it does not stop there. If you see that if the cost is linear regression says, okay, if the cost for this line is 0, then this is the best line. But what this ridge regression is doing is it does not stop there. It's saying that I'm going to have a lambda value and then take the slope. And if the slope is 1.3, then you will have the cost function is 0 plus 1.69. That is 1.3 to the power 2. Right? So which means the cost function is not 0, it is some value, which means it is penalizing a line. I hope you get this point. Earlier, when you only had a simple linear regression, this part was completely 0. Whereas when you added this factor with some lambda value and some slope value for this L1, you can see that the cost function is not 0, but it is some non-zero value. Okay, so now let's consider some small value for slope. Okay, so let us take lambda equal to 1 and slope is also 1. Okay, so what will happen? So this part would be 0 plus 1. So that means you can see that 1.69 is greater than 1, right? So for lower value of slopes, so it is basically penalizing lines that have higher slopes. Why? Because for a small change in X, if the change in Y is too high, such lines are not preferred, because you can see higher slope means that the line is steeper, right? And lower slope means the line is flattening almost. Okay, So basically it means that in ridge regression or L1 regularization, it basically doesn't stop with the simple cost function, but it tries to rather add this regularization parameter, which basically prefers lines that are more flattened. Okay. I hope from this itself it is very clear. I took 1.5 as the, I mean, if the for this same example where the cost was completely 0, C equal to 0, M equal to 1. So in this case, you see the cost was completely 0. So if you see now the ridge regression, what it does is, even though for this line, the cost is 0, it doesn't stop there. It is saying that it should also be a function of slope. Okay. So when you are trying to flatten it, the overfitting problem will be handled in this particular case. Is that clear? Pretty simple. Should I go ahead? Any queries till this point? Okay. If no queries, then I will go ahead. Fine. So we handled ridge regression. Now let's go to lasso regression. Now what lasso regression, a very simple tweak that we do to this particular, so what our L1 regularization helped us to do is get flattened lines as compared to the steep lines. What we did is we were penalizing lines that had a higher slope. Okay. But if you are having this in only 2 dimensions, then this would be written as, can I say, lambda, because we have only one slope, right? So you can say lambda into m square, right? But what happens is this x, generally when we solve regression problems, this x may not be in single dimension. X may be in capital D dimensions. What is the meaning of this? First, let me help you understand this. So what we have here is amount you spent on advertising and sales, right? So let's say I spent 1 lakh, 2 lakhs, 3 lakhs, 4 lakhs. That's the data in lakhs. And sales is, let's say, in thousands. Okay. So let's put it as 200, 300, 800, 600. That's the data set that you have. Number of units that are sold. So if I spend 1 lakh, I'm gaining, I mean, the sales is 200. If I spend 3 lakhs, this 2 lakhs, sales is 300. So this is your X and this is your Y. So our X basically is in single dimension, that is amount only. But let's take an example of the house sales, rent. Okay. So the rent of the house may not be just square feet. So let's say square feet, how much square feet? What are the amenities that you have? Okay. So let's say it has a shopping area or not. It has a play area or not. Okay. And okay, let's put some other things also, and then say what is the rent. So now you see your X is not in one dimension, unlike in this particular case, it is in multiple dimensions. That means each Xi belongs to RD, which means in this case, only let's consider square feet, shopping and play area, which means D equal to 3. So each Xi is in 3 dimensions. If each Xi is in 3 dimensions, what will happen to our line? It will never be a line now. Okay, because your X and Y were in single dimensions, you said it's a line. But when you have a higher dimensional data set, what you have is a plane. Okay, you are fitting a plane, right? So how that plane would look like? Y is equal to, okay, M1 x1, M2 x2, In this case, it is 3 dimensions. That's why I'm taking 3 dimensions. Is that clear? Because my X is in multiple dimensions. In this case, it's in 3 dimensions. Okay. So obviously you will have 3 slopes, as you can see, M1x1, M2x2, M3x3. So in that particular case, what will happen to this equation is you will have M1 plus M2 plus M3 to the power 2. I hope you get this point. Because traditionally, when you go and solve regression problems in real-time situations, you will not have data in single dimensions, but rather you will have data in multi-dimensions. And here I'm giving an example: square feet, shopping area, play area. If these are given, what will be its influence on the rent? Okay, so in that particular case, you will not have just M square, but this regularization part would be lambda into M1 plus M2 plus M3 to the power 2. I hope you get this. Fair enough till here, simple. So which means, so as lambda increases, you have seen that as lambda increases, what happens is our line basically, the slopes of our line is getting near to 0. Okay, the slope is getting to 0 means what? For a unit change in X, there is no change in Y. I mean, it's almost 0. I'm not saying it is equal to 0, but almost getting to 0. That's the meaning. Okay, and what this lasso regression now does is, why lasso regression? Of course, this also helps us in regularization part only. So you have, so let me call this as, so let me rewrite this. So any queries? Why shall we consider a ridge? Okay, when shall we use ridge and when shall we use lasso is the question. Yeah, I'm coming to that. Traditionally, when you apply your linear regression, you will see that there is a lot of test error that is occurring. Okay, first you forget about all this. Now that you understood the simple regression, I apply simple regression. Now I tend to see how much is the training error and test error. Okay, if the train error is very less and the test error is also very less, you must be very happy about it. Okay, but you will notice that of late, when you have almost 0 training error, but the minute you apply your testing data, you will notice that the test error is too high, right? In such a case, now I know this is the time that my simple linear regression would not help. So now you should try to check with a ridge regression. Okay, is that clear? A simple regression, even your test error is too high. Sorry. When your test error is too high, in such a case, you say that I'm going to apply regularization and use ridge regression to control that. And now you will notice that when you use this, we are not just penalizing on the cost, but we are also preferring flattened lines. That's the intuition, geometric intuition. Okay. Now, now let's look at the lasso regression. What is the reason why there's L2 regularization or the lasso regression? So yeah, I think I completely wrote in the previous slide itself. Let me skip this. So now with respect to the lasso regression, what it does is it still has our cost function. Okay, so the cost function would look, it's a very small change that we will do, not very big change as compared to the what I would say ridge regression. So we will make a very, very small change. y hat minus y plus lambda into, okay. This is what we do. It is, instead of slope whole square, we do mod of slope, okay. And how this is going to help? So here, along with reducing the slope, it basically helps us to do feature selection also. So what do you mean by feature selection? Okay, now you have what is the built up area? How much is the shopping area? How much is the play area? Whether there's a school inside the building, I mean inside the community, okay. And then you have what is the rent, y. So this is your x1. So you can say, if you have, this is the first feature, the second feature, third feature, and fourth feature. So you have 4 features for each instance, right? But from this itself, we know that feature F1 should be given more weight as compared to the other features. What the linear regression and the ridge regression does is it gives all the features equal importance, okay. And what this guy does, that's the lasso regression does, is okay, it's going to say that if you have 4 features, then what will happen to this part is lambda into m1 plus m2 plus m3 plus m4, okay. That would be our so what happens is, if this particular feature is not contributing towards your y, that feature becomes 0. Earlier in the ridge regression, I mentioned that some of these m values are becoming close to 0. I never said it is going to 0. I'm saying that these values will be close to 0, okay. Whereas here in ridge regression, sorry, lasso regression, these slopes become 0. So if this feature is not at all important, then the weight that this feature gets would be 0. And if this feature is, let's say, very, very minimal, so this weight would be like something like 0.32. This weight would be something like 0.86, and this would be something like so let this be 0.12. Let this be 0.18. Okay, something like this. Now you will notice that each of these slopes, so these weights actually tell us how much this feature is important. Okay, how much this feature is important. Now you may ask me, how am I going to find out 4 what I would say slopes, right? So when we had a simple regression as y is equal to mx plus c, what we did is we had the cost function j of m with respect to m only, right? So now, since you have multiple slopes, what we would do is we would now take basically the derivative with respect to each and every function, each and every slope. So which means you are basically going to run this derivative m. So this derivative, you will have a set of derivatives now. So you will basically say m1 equal to m1 minus dou of jm by, is that clear? And similarly for m2, you will have m2 minus dou of j of m2 by, and so on. Is that clear? Simple till here? Any queries?
No, ma'am.
Okay. So that's about regression. But let me come to, so let me come to what is the use of this sort of a, regression model. A very, very classic example of this is application of regression in recommendation systems. So you know Netflix, right? So Netflix actually posed a challenge. I don't know, between 2003 to 2009 or 2006 or something like that. So what they did is they gave a set of users and set of movies. So around 18,000 movies and some around 5 lakh users. Okay, so these are the movies in as rows, and columns are users. Okay, the matrix size was about 17,700 cross 5 lakh. Okay, that's the data set that was given. And you can see that some of the entries are given and some of the entries are completely missing. Because as a user, if you see the first column is basically belonging to user 1. Second is user 2, user 3, and so on. This is movie 1, movie 2, and so on, right? So now you can see that as a user, user 1 has only watched this movie and this movie and this movie. Out of 17,700 movies, this guy has only watched 3 movies. Okay, and you can see if you, so whatever movies I have watched, I have given you the rating. So now here, the Y value is basically the, so the Y value basically is the rating itself. Okay, the higher the rating, then I would like to recommend that movie to you. Okay, and you can consider this as a recommendation system, regression problem. The reason for this is the star rating can be anything between 1 to 5. So you must have seen 2.5, 3.5. You'll have a ratings of this sort also. Of course, in this table, in this matrix, you don't see that, but any value between 1 to 5 is okay, right? So that is why we are calling this as a regression problem. So what we do is, when you consider this as a regression problem, we hide some of the, so you can see these are completely sparse data, right? It's a completely sparse data because each user, I mean, in my lifetime, probably we will not watch around this many movies, right? So probably we will only watch few movies and those ratings are given over here. So now what we will do is some of the known ratings are taken away from the matrix. Okay, we will hide this, though you know the values. Okay, we will hide this and we will say that this will be my test data. Okay, and the pink portion of the entries we will call are the known entries only, because what I want is to predict these values. Okay, I'm not predicting all the empty cells over here. Okay, I'm only while constructing, while making my model, I am only treating these as a training samples, okay, and this as a test sample. Now you build your regression model and try to predict what is this value, okay. So, but at the background, you already know these values, okay. So you are saying this is my predicted rating of user X item I minus, so this is the predicted minus actual, because you know background mein what is the value. Okay, so for all the what do you say, unknown test examples, okay, I am trying to compute what is the error I am trying to make. This is what you saw earlier, right? Sigma I equal to whatever. Okay, this is very, very, very classic example of recommender systems problem. I mean, this Netflix data is available. IMDb data set is available on the Python library. So probably you can try. One of the things that I could suggest is, you know, you can run multiple algorithms and then try to see whether which of these. So this is called as root mean square error. Okay. And whichever model gives us the lower RMSE, we can choose such, what I would say, lines or such models which give us the lower RMSE. So now what you do is, okay, so let me give you this trick that I use. If I'm given with 1 lakh training examples, okay, what I do is I split this into train and test. As you can see here, few of them are train and few of them are test. So the problem with this approach, as I go along, you will notice that first time, okay, so first let's assume this 70% are used as train and these are used as test. But the problem is this may be biased, and one single run may not give me the entire gist of the model that you have constructed. This is an implementation issue. Okay, so what you basically do is, don't just run this and say this is my RMSE or this is my mean squared error. Okay, so what you basically do is run this experiment multiple number of times, taking different train. So make this as a train now and make this as a test now. Okay, and then get your RMSE. You get one RMSE from here, one RMSE from here. Split this multiple times, randomly split this 1 lakh examples into train and test multiple number of times. So what will happen is, when you do this random sampling, it gets shuffled. The train and test get shuffled, right? So yeah, this is one of the tricks that Keglers generally use. Okay, so what happens in these Kegel competitions is that they generally give out these training examples, and then they ask you to apply it on a test example. So better thing is combine both of them. Okay, test and train, combine both of them, and then do this like 10 times or 15 times. Okay, experiment the same model, build the model with different train and test 10 to 15 times, and you will see that the RMSE reduces as much as possible. At least you will get a 5% difference when you do this. This is one of the tricks that many Keglers use. Okay, even I do that. Okay, remember that when this sort of a sitting is given, shuffle the train and test, and when you publish your RMSE, you say that categorically you must mention that I ran this so many number of times, and the average RMSE, and you have an RMSE from this train and test from this, so you can call this RMSE 1, RMSE 2. So you have 10 RMSEs now. Take the average, and that would be the best model that you construct. Okay, is that clear? Fine. So I just completed the regression model. So we said we started with supervised learning. We said given xi, yi, I have to learn a function f of x that maps to y. And towards that, we saw linear regression, we saw ridge regression, as well as lasso regression. Now let me move on to the next topic, that is logistic regression. So this name is completely misleading actually. Okay, don't think this is regression. Okay, now I'm moving to classification. Fine, let me keep track of time. Okay, I am moving now from logistic from regression to classification problem. So I mentioned earlier that when you have your data set that is given to you, so you have each xi comma yi. Now just assume that you are given this example of rental problem itself. So square feet, shopping area, play area, and so on, and whether this this particular property would be taken by the customer as rent, yes or no. Okay, if this is the case, then my yi is basically a binary classification problem. Okay, so this is my x, x1, x2, x3, right? 3 features, and you have the class label that is y, which can take only 2 values, yes or no. Since this is a discrete value, you can simply say that this is a classification problem. But you may ask me, if it is a classification problem, why that name regression? Okay, so we just now understood that we have an equation y is equal to mx plus c that we are going to fit. But the problem with using directly that equation for classification is that this y value is a continuous value in our previous case. But here y should either be 1 for yes or 0 for no, right? Which means my y can take only 2 values, but I'm going to use that same regression in order to see that y value will be restricted between 0 and 1. In the previous regression problem, y value is unbound. The value of y could go, it has no bounds, right? Whereas here, what I'm going to do is I'm going to restrict the y value between 0 and 1. So how do I do that? So in order to do that, we will use a sigmoid function. Okay, so what is a sigmoid function? The behavior would be something like this. Okay, and the sigmoid function, you can get this sort of sigmoid function by writing 1 over 1 plus e power minus x. Okay, so when you do this, basically you have the y value, which is ranging only between 0 and 1. And you can say that when y is greater than 0.5, I will say the output is class 1, which is yes. And when y is less than 0.5, we can say it belongs to class 0. Okay, that's the threshold. Fine. So we can say whatever regression, so you apply your regression, you get this model, right, which is basically a line, right? You get this model, which is basically your line, and then you try to apply this using this sigmoid function. We are restricting y value. Okay, we are restricting the y value, and you can see that it's no more a line, but it's a curve, right? So because it's a curve, let's assume that the c value is 0. Okay, let's assume that c value is equal to 0. So our model basically is now minus mx. What is our y? Y will be 1 by 1 plus e power minus mx. Is that clear? Only trick I played is y equal to mx plus c. Y becomes very, there's no bounds on y, what value it should take. But for this classification problem, especially the binary classification problem, I want it to take a value 1 or 0. That means there should be bounds on y. So I'm saying it can take a value 0 or 1, any value between 0 and 1. So when you basically apply this sigmoidal function, generally for a sigmoidal function, we write 1 over 1 plus e power minus x. Okay, so I just applied that. And my x here, my model here is minus mx. Okay, you apply regression, you get some m value. So you just apply a sigmoidal function. Now you compute your y hat, which is predicted value. If your predicted value, I already know that my predicted value can be between 0 and 1 because of this. So when you are having this predicted value, you see what is the predicted value. If it is greater than 0.5, you say it belongs to class 1. If it is less than 0.5, it belongs to class 0. Very, very simple trick that we play. And now you see, that is why we call it as regression, because it is using regression model. But this is a classifier. Don't get confused by looking at the name. Is that clear?
Yes, ma'am.
Okay. You can stop me in case things are getting out of your control. Okay, I will slow down. Yeah. So now the next model that we are going to learn is basically the naive-based classifier. So most of the, when I name a few classifiers, there are multiple classifier models. Just now we saw logistic regression. There's something called as support vector machine, decision trees. There are many more. Okay, so I'm only going to talk about logistic regression and the naive-based classifier. So what generally, when we talk about classifiers, there are two types. One is discriminative classifier and the other is generative classifier or probabilistic classifier. So logistic regression is basically a discriminative learning. Basically, it is trying to find a line that could separate the positive points and the negative points. Whereas in case of the generative learning, what it basically does is it tries to learn some of these parameters. Okay, let me show you what I mean by that. So first of all, let us now try to understand what I would say, how this naive Bayes tries to formulate this problem as a classification. So suppose you have two events, A and B, right? And so according to because it's conditional probability, the way we write is probability of the event A occurring given that B has already occurred, right? That's a conditional probability. So this is expressed as, according to the Bayes rule, we can write it in this particular form, okay? I wouldn't say a Bayes rule, but basically it's a conditional probability. So if you want to find the other way around, probability of the event B occurring given that A has already occurred, still it will be something like this. Okay, so which means this is the intersection and this is B, right? So what we do is, let's basically apply the Bayes rule. Now what Bayes rule says is, if you are given this conditional probability, we can estimate this conditional probability as B given A, okay, into P of A by P of B. That's your normal Bayes rule, where we call this, so we call this as data or evidence, We call this part as prior, and we call this as likelihood. And this is called posterior probability. Okay. Now, so this is our normal Bayes rule. But what we are trying to do is basically how do we apply it for classification problem? Okay. So what we want to basically estimate is what is the probability of the class label Y, okay, given that my X is given as X1, X2, X3, and so on, XD, right? Because our features are in D dimensions. Previously, I showed you square feet, shopping area, and so on, right? So if the multiple dimensions could be there. So what I want to compute the probability of class label Y given this data in D dimensions. How can I write this using the same notation? Here it was A and B. So now this is the data set and this is Y. Can I write this as probability of X1, X2, and so on, XT given Y, right? So this is my B, this is my B, this is my A, right? Into probability of Y over probability of X1, X2, and so on, XT. Isn't it? Pretty simple. But here is the problem. In the likelihood, you have so many probabilities, right? You have so many computations to do, right? So what we do, so just assume that if you have only two features, X1, X2, and then Y. So how many possible combinations are there? You have 0, 1, 0. If you have only binary feature, okay? If your X is binary, if your feature is a binary feature, so you can see that there are 4 combinations, right? Similarly, if you have X1, 3 features, you'll have 8 combinations. Just think of D features. So which means basically you will have to compute 2 per D possible combinations, which is highly difficult. Okay. And here comes that assumption called naive assumption. Why is this called naive assumption? Because if you break this as a chain rule, it's going to be very, very difficult. So we make this naive assumption, which says that each feature is conditionally independent of each other. So when we have that conditional independence, then writing this is very, very easy. So I can write this as probability of x1 given y, and it does not depend on x2 or vice versa. So I can write this as x2 given y and so on, xd given y into probability of y over p of x2 and so on, xd. So the thing is, this is data set, right, which you are, or evidence, which you are trying to multiply as 1 by p of x1, x2, xd, you are trying to multiply to all classes. So we are trying to compute what is the probability of y1 class, that is whether the guy will take the house for rent or not, okay, given x1 to xd. You have to do it for x2, y2 also, y3 also, if there are multiple classes. But this is a constant that you will be multiplying to 1 over some value, which you will be multiplying to all classes. And we want to have as less parameters as possible. So we can ignore this part. So finally, what we will have is only this part. Okay, you can write this also. This can also be written as, okay, p of y multiplied by I equal to capital 1 to here, how many you have? D, right? So you can say p of xi given y, isn't it? So it is D such things. So this is what you get. Let me show you with an example. I think I have an example. So you have 3 flavors of naive Bayes classifier. Okay, that is Bernoulli naive Bayes, multinomial naive Bayes, and Gaussian naive Bayes. When to apply each of them? So if your each feature is binary feature, that means your feature f1, f2, f3, if these guys are binary features, then you apply Bernoulli naive Bayes. When you have your features as a discrete counts, for example, you do sentiment analysis or something like that, then you apply a multinomial naive Bayes. And if your feature is, let's say, height, weight, and something like that, or blood sugar, and you have taken all parameters of a patient and you want to say whether this guy would have a cancer or not. Okay, something of this sort. So each feature has a continuous value, right? So then you apply naive Bayes. Very, very simple. So here's an example of what I wanted to show, how we do that. This is the data set, a standard data set from a textbook. You have multiple, and generally I said each feature is binary or each feature is multinomial. But traditionally, neither of them happen, as you see an example here. One of them is not just a binary, it is something. This is also not binary, it is something. This is binary, while this is also not binary. Okay, so we do a combination. Okay, so here's an example. These are training data 1 to 14, and this is your test data. Okay, so you compute what is the probability of y1 and y2. So what is y1, y2? You have 2 classes, C1, C2, that is represented as here in the slide, where C1 equal to yes and C2 equal to no. Okay, so P of yes would be 9 examples. So there are 14 examples, out of them 9 are yes and the rest are no. Okay, that's the probability of prior. I said P of y1, P of y2, they are prior, right? This is your prior computation. And then you need to do this computation, that is P of this computation, right? These computations. So for those computations is basically what, so I don't need to do for everything. What I'm doing is only for this is a test data. I need age, income, and whether he's a student or not. and then whether his credit rating is fair or not. These are the examples that are given. So I will only do for youth. I will not do for everything. Okay. So you can see whenever there was youth, age equal to youth, how many of them were yes and how many of them were no. So you can see 1, 2, 3, 4, 5. Okay. 5 examples. Out of that, 2 examples were no. And the example, 3 examples are no, and 2 examples are yes. And that's what you can see. 2 examples out of 9. What is 9? So how many of them are belonging to basically your yes instances? C1 instance. Okay. So out of where class is equal to yes, out of them, how many are youth? Okay. And no are 5. So out of 5, how many are youth? Okay. So I showed you for one, you need to do the rest computations like this for the other feature, income equal to medium. So you see 1, 2, 3, 4, 5, 6. Okay. So out of those 9 examples, how many are income equal to medium? These 2 will be 6. Addition of these 2 would be 6. Okay. So out of this 6, how many have class label as yes and how many of them are class label no? So you need to do that computation. Once we do that, in order to find the likelihood, we need to basically say probability of, I think it should be the vice versa. Y is equal to s given x would be, you need to just multiply these corresponding probabilities and you are getting what is the probability that with this x, the guy is going to buy a computer. So you got some value. Similarly, for no, you also will do a computation, right? And we basically have another part which is basically called as argmax, which basically says that what is the maximum out of these 2, right? So in this case, the maximum is yes. So then we say that this guy is going to buy a computer. Okay. Is that clear? Fair enough. So if you give me 5 more minutes, do I have 5 more minutes?
Yes, ma'am.
Yes, ma'am.
Yeah. In that case, I will basically, yeah. So the last part that I would like to talk about is this 9 ways is a very, very good classifier when we talk about sentiment analysis. So here's an example that I would like to show about some iPhone. So there are certain text that is taken, and 9 ways is very, very good for most of the text-based applications. So here's a sentiment that is expressed. Now I would like to say whether this sentiment is a positive sentiment or a negative sentiment or a neutral. Okay. So in that case, what we do is, so to avoid the delay, I just wrote everything because I knew that I might run out of time. So here you see that given each sentiment is considered as a document. Okay, each sentiment is considered as a document D with n words. Okay, with n words. And here you have a class label C, which is either a positive sentiment or a negative sentiment. So 0 is negative and 1 is positive. So you have 2, what I would say, class labels. Okay. What you're trying to compute using this naive Bayes is what is the probability of a sentiment being positive given these n words. Given these n words. Now you apply your traditional Bayes rule as I did earlier. So your probability of sentiment, probability of words given sentiment multiple. This is your prior. I wrote prior earlier. Okay. This is your P of Y. This is your conditional probability. And you have n such words. And then you have evidence. Now, as I mentioned again, the evidence is a constant. So generally we ignore the denominator. Because whether it's positive sentiment or a negative sentiment, 1 over P of W1 to W1 will be multiplied to both classes. And hence, it is not going to make much difference. So we ignore this part. So we say when we ignore this part, that is why I'm writing here, it is not equal, it is nearly equal. Okay, this probability is nearly equal to this probability. Okay, but the problem here is I am trying to, this is product of I equal to 1 to n. So if one of these words has a zero value, everything becomes zero because we are multiplying. So what I do is instead of multiplication, I take log on both sides so that I'll be converting the log, product to sum. The minute you put log, you can convert that product into sum. Okay. So now the whole question boils down to how do we get these values? P of Wi given the sentiment. Okay. So in order to do that, let's have a look at this. So you are given bunch of training examples where each, sentiment is given, and whether it's positive, negative, that is also given. So n such training reviews along with their sentiment, whether it is positive or negative, are given here. Okay, so how to compute what is the probability of a positive sentiment? The probability of positive sentiment will be number of documents in the positive class or total number of training examples. Okay, pretty simple. Similarly, negative class also you can do the same thing. Number of documents of class C equal to 0, right? C1, C2, C3, as many as you want. If you want to make it as a more complex thing, you can still have it as positive, negative, more negative, negative, neutral, positive, more positive, right? You can have multiple things. But here the computation would be number of documents belonging to that class. If class I am talking about is positive, C equal to 0 or 1, depends what you're trying to. So then let us look at this part. So you know how to compute this part. Now let's see how to compute this part. This part would be count how many times this word Wi occurred in the positive class. Okay, divided by total number of words that are available in the entire dictionary. Entire dictionary means that you need to find out from these all documents how many unique words are there. That's the count part over here. Okay, but sometimes the counts may be negative, 0. Okay, so traditionally these are the alternatives to overcome that 0 part, because plus you either add +1 both to numerator and denominator, or add 1 to numerator and then add the number of unique words in the entire reviews to the denominator. That's also possible. So this is called smoothing in natural language processing, just to avoid that very, very minimal values or close to 0 values, because generally we take a product or to overcome that small probability values, we add either 1 or the number of words in the entire, unique words in the entire review. Okay, and this is how this is an application of how naive Bayes is actually used in product reviews, or you can call it sentiment analysis also. Okay, I think that's all. But the reason why I picked up this model is basically it's very, very, even though you have a lot of noise in your data, this particular model seems to extremely do well. Okay, and even if you have a lot of missing values, you can still work with this. But there are cases sometimes when the independent assumptions may not work, but there are many more higher models called Bayesian belief networks and so on, which you can explore. Okay, so that's all I have. In case you have any queries, I'm open to questions. Thank you.
Yeah, thank you, madam. Thank you very much. Yeah, my dear participants, please, anybody wants to interact, please interact. I already posted 3 to 4 times in the chat that if you have any questions, you can post in the chat. Now, you are free to interact with madam by unmuting yourself. Dear participants, yeah, it seems no questions, madam, from the participants.
Thank you, sir.
Yeah, thank you very much, madam,
Thank you.
for
Thanks a
your
lot.
kind consent and sparing your valuable time with us.
Thank you, sir.
And
Thanks
really,
a
like,
lot.
it was very practical, madam. You have shown, like, complete all the regression equations apart from the practical analysis. You
Yeah.
have covered both the supervised learning with the various all the
Because these
classification.
are two very basic, things that they should know. So that's why in the limited time, somehow I tried to squeeze it. I'm sorry
Yes,
for
madam.
if I have just, at least the last part, if I've just squeezed in 5 to 10 minutes.
Yes. Today afternoon we are going to have.
Yeah, I saw the schedule
Yes.
and then decided that if this is given, then it is very helpful for
Yeah,
people.
especially for beginners or even for the people who are having a reasonable experience.
Yeah.
These are the very basics and in fact very important.
Yeah.
As you said, once if they are good at this, then remaining things they can manage.
Okay. Thank you. Thank you
you,
very
madam.
much for patient listening for about 1.5 hours.
Thank you, madam. Now, just 1 minute, madam. Now I
Yes,
request our Madam Radhika. 1 second. Madam Bhavana to propose vote of thanks for this session.
Good morning to all. Good morning to madam. Ma'am, it's my privilege to propose vote of thanks for third day morning first session on 1 week online as ISTE-STTP on machine learning applications research challenges 2020. We have been very fortunate to have you as such a great eminent speaker who has explained us in a good way and a practical ma'am. It is a very good practical session. Actually, we have remembered our olden and memorable days by doing this all the calculations and things. Uh, it is very fortunate, ma'am. And ma'am has discussed about the various traditional programming and machine learning, and also ma'am has discussed about the types of learning, and also she has discussed about the supervised learning and the various problems like overfitting, underfitting, and ma'am has discussed about the various regressions such as ridge, linear, lasso, logistic, navi-based classifiers, as well as ma'am has discussed about the three flavors of navi-based such as Bernoulli, multinomial, Gaussian, and also the good examples such as the sentiment analysis on the navi base. And it was a great it is very great, ma'am, to have you here, and it is very fortunate that we have got you such a good speaker, and we have gained a very good knowledge about what is supervised learning and all. Thank you, ma'am. Over to Dean, sir.
Thank you, sir.
Thank you,
Thank
once
you.
again on behalf of our
Bhavana.
institution and on by personal behalf
Thank
for
you,
your
sir.
kind consent and sparing your valuable time, madam.
Thank you. Thank you very much for providing me this opportunity, sir.
Thank you, madam. It's our pleasure,
Thank
madam,
you.
because you have become a wisher to our institution. You are here for the conference also.
Yeah.
So that
Thank you.
since we are having liberty to request you at any point of time as per the requirement.
Yeah. No
Thank you,
problem.
thank you very much.
Thank you.
Thank you.
Thank you.
Thank you. Dear participants, I request you all, next session will be at 11:15 sharp. Now we have 3-4 minutes, around 5 minutes you can take break. Okay, now already time is close to 11:10. Okay, because as we are staying at our house only, if you want you can relax and be sure by 11:15. Today's second session, Dr. S. Viswanadha, who is the resource person for our session today, who is Professor of CSE, JNTUH, Vice Principal, JNTUH, College of Engineering, Jagtial. Dr. C. Krishnadi Garu, who is the Director of our institutions, my coordinator, Dr. K. Rameshwari Garu, other heads and departments, heads of various departments, Dean School of Engineering, Dean School of Pharmacy and MBA. My dear participants, very good morning to all of you. It's my privilege to introduce today's resource person of this session. Dr. S. Viswanadha, presently working as Professor of CSE and Vice Principal, JNTUH, College of Engineering, Jagtial, who has 24 years of experience in teaching, research, and administration. From December 2016 to till date, he is serving as Vice Principal, JNTUH, College of Engineering, Jagtial. He has served as Director MCA, GRIET from June 2008 to July 2010. From April 2011 to April 2015, he served as Head of the Department of CSE, JNTUH, College of Engineering, Jagtial. He obtained MTech from JNTUH, Hyderabad, PhD from Acharya Nagarjuna University, Guntur. He is certified CMI in Education, Leadership, and Program Management, which is sponsored by MHRD, AICTE, and UKRI, Dudley College, London. He has been honored with State Best Teacher Award 2020 from the Government of Telangana. Best Computer Science Engineering Award from ISTE, Andhra Pradesh for the year 2014. Certification of Appreciation Award in Independence Day celebrations from Honorable District Collector Jagtial in 2019, and Best Citizen of India. His research interests include programming methodology, machine learning, algorithms, biometrics, and quality in higher education are globally recognized. He filed 10 Indian patents deriving from his research and relevant to educational institutions. His research contributions are not only confined to his subject area, but also extend to other related domains arising out of the new education system, assessment, and accreditation, and their impact on Indian higher education. To add impetus to his academic credentials, he has undergone training as well as speaker for the quality improvement in education at NITTR OSA 2012, which is World Summit on Accreditation 2012, World Summit on Accreditation 2014, TCS, Infosys, and NBA and NAC. He guided 10 PhDs and 5 PhD scholars pursuing under his able guidance. He is a life member of ISTE, IET, CSI, and IAC-SIT. He has 120 plus research publications in his credit in most reputed international and national journals, which includes Scopus, SCI, and Springer, etc., and even conferences. He has authored 4 books and 11 book chapters and implementing 2 AICTE-sponsored research projects, 1 TechWhip project, and 1 fellowship from Telangana State and Science and Technology. He has been a member of several government committees, JNTUH, AICTE, NBA, NAC, etc. He delivered more than 70 invited talks, expert lectures, and keynote addresses on various technical topics as well as outcome-based education, NBA and NAC accreditation process in the country and outside the India. He has organized several workshops, seminars, tutorials, and conferences. He has visited Singapore and Taiwan and interacted with several academicians and researchers. Once again, I'm telling you, it's my privilege to introduce about today's resource person. With this brief introduction, I warm welcome to our resource person, Dr. S. Viswanadha. Over to you, sir. Thank you, sir. Thank you very much.
Yeah, thank you very much, Janardhan.
Thank you, sir.
So, shall I proceed?
Yeah, please, sir. Yes, sir. Sir, you can share your presentation. Yes, sir.
So, is it full screen or partial screen?
Partial screen only, sir.
Yeah, now please.
It is okay, sir, now.
Thank you. So, Very good morning to all my dear participants and eminent personalities. So today I'll be going to talk about a basic introduction of the machine learning, and I'll move from the basic introduction to the artificial neural networks. So why should I start with the basic introduction means? So this is the very important, why should I move from the basic machine learning concepts to the artificial intelligence? Okay, artificial neural networks. So in today I'll be going to cover half of the topics, and tomorrow I'll be cover remaining half of the topics. So what are the topics I'll be going to read out? The first I start with the introduction of the machine learning. Why is it called machine learning? And I'll take a certain examples for understanding of the machine learning concepts. And again, I'll be going to compare with the traditional programming and machine learning. So we all have a doubt, what is the difference between the traditional programming and machine learning? And again, I'll be talk about the categorization of machine learning. So then I'll move to the, why should I go further from machine learning to the deep learning? So the difference between machine learning and deep learning. Then I'll give the most information about the uses of the deep learning and also how deep learning follows the neural networks, artificial neural networks. And I'll be going to explain with the example regarding the perceptron. So this is a playing key role in our artificial neural network. So once you understand this concept, then I think it is very easy to remember and easy to implement artificial neural network concepts. And I'll be going to take certain examples which we are very familiar, logic gates. So that I think logic gates we are all very familiar. You know that binary gates, and other gates also is there. So I'll be going to explain AND gate, OR gate, NOT gate, exclusive NOR gate with the help of the artificial neural networks. There are two different types of neural networks, are the single layer neural network and multi-layer neural networks. But in today's session, I'll be going to end with the single layer neural network. In tomorrow's session, I'll be going to share the multi-layer neural network concept. These are the topics I'll be going to cover in today's session and tomorrow's session. Okay. So first I'll start with the definition of the machine learning. I think you are aware of it, but I want to share, I want to bring you to my topic. My topic is artificial neural network. Okay. The machine learning is an application of artificial intelligence that provides the system the ability to automatically learn and improve from experience without being explicitly programmed. So what I want to do, I want to design an intelligent machine. I want to design an intelligent machine like a human. So this is what our aim. In the future, you can see such a kind of machines. So whatever you want, you can get with the help of the machine rather than getting with a person. So this is the environment we want to create, and we want to see that also in future. The next, we could not find any standard definition for the machine learning. So just we want certain key terms. Based on the key terms, by using your own connectors, you can define yourself. So you cannot find anywhere the standard definition. Another possible definition is, see that the primary aim is to allow the computers learn automatically without human intervention or assistance. You see that? So this is our aim. So without human intervention, I have to develop automatic machine. So I'll give an example. Suppose if I visited last 1 week to your home, you offered me coffee or tea several times. The next day, if I visit your home, then what you need to do, you need to predict yourself. Why you are asking again, would you like coffee? Would you like a tea? This kind of system we want to adapt. You see that once I can install a machine in my home, if you are going to visit maybe 10 days, 15 days next, then my machine will record your information. In the 12th day, my machine will be decide, and that will be automatically predict what you are going to expect at that time. That will be decide, that will be going to provide to you. So this is the environment maybe we can see in the future. In the future, we never ask what would you like. So maybe machine will be predicted and it will be take a decision. So let us see, here is one more example, a service. A new songs or artists to recommend to a listener, machine learning algorithms associate the listener as per the preferences with other listeners who have the similar music taste. So this is what you see that I observed recently in the Facebook also. I have gone through the nearly 20 videos, and the next day I used to get the similar kind of videos. How am I getting? Because of the past experience only. So what I have seen in the last 10 days, similar kind of videos. So I have watched the several videos regarding the machine learning. The same kind of videos I'm able to access in the Facebook also. Facebook is also already following this machine learning concept. When you see certain kind of videos, based on that, the Facebook people are predicting, oh, this person is want this kind of music, this person want this kind of videos. Based on that, they are also suggesting to us knowingly or unknowingly. This is what the system is adapted in the Facebook and LinkedIn also. So next point is, why is it called machine learning? Why is it called machine learning? It is used to be called statistical learning theory. So what we need to do, when I want to understand the machine learning, I must know the probability and statistics. And also common sense is very much important here. Without common sense, how do I predict what is going to happen in the next minute if I am in the certain situation? There I should apply the common sense only. So like that, you see that here, when I want to really understand the machine learning concepts, I must know the statistics, I must know the linear algebra, and also common sense, very much important for understanding of the machine learning. So that it is used to be called statistical learning theory. It's because the way human learn different thing machine is a learning different thing. You see that. Why we are not discussing machine what to do? We are not discussing what to do. We are discussing how to do. This is very much important. You see, even when we compare with the traditional education system and outcome-based education system, in the traditional education system, what we are focusing, what to do. But in the outcome-based education system, how to do. A similar fashion, in the traditional programming, what we are focusing, what to do. Okay, there is a input data is there, and I want this output. So then how to get that output only. For that, what we are doing something, we are writing a program, and finally we are producing the result for several possible cases. But we are not much bothering about that, how to do process. So here what we need to do, we are discussing machine, how to do. So machine will use this skill to solve next problem it will face without explicitly programmed. So what we are expecting, the machine will use this skill to solve the next problem it will face without explicitly programmed. Let us see what I have been given one example. If my friend is going to visit tomorrow, so the machine has to be use the previous day's skill. Without concept, without explicit interaction also. So this is what you see that process we want to introduce. So I'll be going to explain with very simple examples. I think we might be very familiar. These are the examples we might be seeing in the 9th standard and the 10th standard. You see, so in those days we learned a little about the machine learning, knowingly or not unknowingly. Let us see in this simple question, 2, 4, 8, 16, and so on. So what is the next number? What is the next number? How you are predicting on the basis of the input and output? On the basis of the input and output. You see, so input and output, you are predicting what is the next number. Otherwise, I should not able to predict it. You see, 2. What is this means? You see that 2 power 1, 2 power 2, 2 power 3, 2 power 4, and so on. So then what is the 2 power x? So x is equal to 1, 2, 3, and so on. So this is what you see that next number is, you are predicting with the help of the input and output only. Suppose if I have only two numbers, but I don't have 8 and 16. You see that if I don't have the 8 and 16 with the two numbers, we are able to predict properly. It is very difficult. Why? Maybe 2, 4. Next, maybe alternate numbers may be there. So how do I know that? So that I must be required minimum certain number of sample input and output values. Without minimum number of sample and sample inputs, that could be very difficult to predict what is the next. So that you see that with 4 numbers, I am able to predict. With 2 numbers, I should not be able to predict what is the next. So there is an ambiguity. So for the minimization of the ambiguity, I need to get the more number of sample inputs. The similar fashion, even the machine learning also, if you can increase the as maximum as the number of samples, then you can get predicted 100% accurately. Otherwise, it may be certain percentage of accuracy only. Like another example, you see that 1, 3, 7, 15, 31, and so on. So what is the next number? You see, 1, 3, 7, 15, 31. This means 2 power 1 minus 1, 2 power 2 minus 1, 2 power 3 minus 1, 2 power 4 minus 1, like you see that, and so on. So then what is, you see that next number is 63. So then 2 power x minus 1. You see that now with the help of this function, you can find any position value. Suppose x is equal to 20, x is equal to 10, x is equal to 40. Like this, you see that you are able to get the value with the help of this function. So how I have been defined this function with the help of input and output values only. If I do not have any input and output, then I should not be able to define a function. So this is what a simple process of the simplified view of machine learning. What we discussed, with the help of certain series of numbers, we defined a function. That function is, I can say it is a mapping function from the input to output only. So I can say the machine learning concept is you are creating a bridge between input and output. But that bridge, how it is a quality, that is what we are measuring with accuracy only. So this is what we want to consider. So when we have the input data and output data, now I am creating a bridge. A bridge is called a function. A function is called a mapping function between the input to output. So for prediction of the future outcome for the next element. So this is what you see, that data is there, and based on that algorithms, finally you are developing a mapping function between the input and output. And this function, we can use it for the next future requirement. So another example, you see that given a set of numbers, you see here, I have a certain set of numbers, maybe single digit numbers, 2-digit numbers, 3-digit number, 4-digit number, whatever it is. But for understanding purpose, here I have taken a small set of numbers only, randomly. So 27, 26, 17, 13, 25, 34, 5, 8, 92. These are the numbers I have. Now my aim is what you see that, my aim is I want to partition into 2 sets. My aim is what? Partition into 2 sets. In this case, do I need to apply the supervised learning or unsupervised learning? This is what you might be learned in the previous sessions. Now, do I need to apply the supervised learning or unsupervised learning? So because of here, it is the data is the unlabeled data. So that what I need to do, I have to be apply the unsupervised learning method. My aim is what? Partition into 2 sets. Okay, as per my assumption, as per my idea, what I did, odd numbers I made as a one set and even numbers as another set. But as per my opinion, but X opinion may not be similar to my opinion. What is expecting? You may be expecting single digit numbers as a one set and 2-digit number as another set. You see that like people mindset is vary, but my mindset is odd numbers and even numbers, and X mindset is the single digit number and a 2-digit number, or maybe third a Y person, maybe you want prime numbers and non-prime numbers. Like you see that hundreds of persons are raising by the different experts. So this kind of system I want to introduce, whatever they're expecting as per their requirement, I should provide the solution. That is what the importance of the machine learning. Here is just partition into 2 sets. This is what we need to predict. How the person is going to, what person is going to expect from me. I have this list. He is asking only 2 sets only. 2 sets means he may be expecting 2 different prime numbers, non-prime numbers, Fibonacci numbers, non-Fibonacci numbers. Yeah, even numbers, odd numbers, single digit numbers, 2-digit numbers, like many are there. So this is what we have the problem. For this, we need to develop automation system. So I think, why this? Why not single and 2-digit? You see that you might be given two lists, but as a leader, as a team manager, I may ask one more doubt. Why not single and 2-digit? Similarly, both mine and your solutions can be right, but your solution is right. My question is also right. What you need to do, you need to provide as per the user requirement only. So hundreds of users are there in this society, in this world. So what they are going to expect? We need to predict, we need to provide the better solution for them. So that is the aim of the machine learning. The differences between the traditional programming and machine learning. You see, in the traditional programming, what we used to do it, so there is the input data and there is a problem. And then we are trying to writing an algorithm or maybe developing a program for a certain output. So that is what traditional programming system. Traditional programming system is input data is there and problem is there. And then I'll be going to write a algorithm or maybe developing a source code. For what purpose? For output. So here we are checking output only. So we are expecting exact output. We are writing an algorithm for the exact output only, not for any with deviation output. Okay, so this is what the traditional program. But whereas in the machine learning, let us see here is, we have the input data, we have the output data, we have the input data and output data. Now I want to develop a program. So with the help of the input and output, I have to develop a mapping function. A mapping function. That mapping function, I can say it is a program. It is a program. So that mapping function may not be 100% accurate. So it depends on the sample size of the input data that could be giving the accuracy level. So that is what we might be going to study, how to improve the accuracy when maximum number of samples, if we can increase the number of samples, then accuracy level also will be increased. You see that. How do I predict your character? Suppose with the last 1 week we had an interaction, we are able to predict 100% accuracy, what you are going to take action in the next minute, it is very difficult. If I have an interaction with 1 year, then I could able to predict, I think 50% is correctly. So if I had an experience last 20 years, definitely I can predict what you are going to take action in the next minute, approximately that is 75% or 90%. This kind of process we are doing, you see that. Once again, I'm repeating, machine learning is what? We have the input data and output data. Now we want to create a bridge. We want to create a bridge. A bridge is called a machine learning program. So with respect to the availability of the input data and output data, I created this bridge. This bridge may or may not be effectively useful for the new incoming data. So how do I make it effectively? When adding new data, for that also I have to be considered and I have to strengthen the which I developed earlier. So that is what machine learning. So once again repeating please, machine learning, I can say it is a bridge between input data and output data. And always the machine learning algorithm or maybe program, it produces the accuracy value only, predicted value only. But whereas in the traditional programming, it produces exact output value only. But machine learning will produce only accurate value only or predicted value only. So that is the basic difference between the traditional programming and machine learning programming. So categorization of machine learning. So you might be familiar about categorization of the machine learning. There are three different categories are there. One is the supervised learning. Second one is unsupervised learning. Third one is a reinforcement learning. So there are three are there, but in this slide, I'm going to share with you only two methods. Just I'm giving briefly. So what is mean by supervised learning and what is mean by unsupervised learning? The supervised learning means pre-categorized data. So I can apply the supervised learning only for the labeled data. Unsupervised learning algorithms, I can apply for the unlabeled data. Unlabeled data. So this is what you see that. So I have one friend, if he will tell, okay, tomorrow I'm going to do this, so I can predict it, something. If he is not going to tell, then what should I do? What he is going to do? That is what I should predict it. So this is what you see that supervised learning and unsupervised learning. In the supervised learning category, there are two different mechanisms are there. One is the classification, other one is a regression. So classification and regression, I think you might be known that, but I'm not going to give much information about this. This classification is also I have to concentrate on the categorical data. This regression, I have to be concentrate on the numerical and what it is going to happen next minute. Unsupervised learning, unlabeled data. So I have to apply the unsupervised learning for unlabeled data. Supervised learning methods, I have to apply for the labeled data. So here I have given certain examples. Let us see. First, we will discuss about the definition. Then I'll go for the real world example for understanding of the supervised learning method. What is the definition of the supervised learning? Let us see here. It can apply what has been learned in the past to new data using labeled examples and predict future events. You see that whatever the previously data is available, based on that data, I have to develop a model. With the help of that model, I have to predict for the future. This is the supervised learning. Let us see here is I have given some sample data. So two objects are here, two objects are there. Here labeling is there, male and female labeling is there. So then we see that with the labeling, I can easy to classify. How I can classify male and, so if I want to classify into two categories gender wise, so with the help of this labeling data, I can easy to classify male category and female category. When the problem is there, suppose you see that in this example,